Hello everyone and welcome to another video. Today, I'd like to discuss the relationship between pole locations of a dynamic system and the associated performance of that same system. In a nutshell, I'd like to establish a relationship between the locations of the poles and parameters like the percent overshoot, settling time, damp natural frequency, etc. of a dynamic system. If you've been following along with our series on controls, then you know that one of our previous videos actually discussed in detail the concepts of percent overshoot, settling time, etc. Therefore, if you haven't had a chance to watch this video already, I would recommend you stop, watch that video first before continuing with the lecture today. So, if all of this sounds good to you, why don't we jump over to the whiteboard and get started. Alright, so like we said here, the goal today here is to discuss the relationship between pole locations and system performance. So the picture that goes along with this is, let's say you've got some plant here, or some dynamic system, maybe let's call it a G of S, right? And there are some inputs here, U of S, and some outputs, Y of S, or time, whatever. If you want to look at this in the Laplace of the time domain, it doesn't really matter. But conceptually, what we see here is this system has poles here, right? And if we were to plot these poles in a real imaginary plane here, in this complex plane, we understand that the poles, depending on where the poles of this system are, sort of affect how the performance of this system or what the output of this system does. So for example, right, if you had a pole, you know, here on the real axis, but in the left half plane, we know that thing is stable. And if we were to plot, you know, very roughly like y versus t, right, we know that it would probably sit here and decay, right? And we know that if the pole was even further in the left half plane, right, for a similar input, you would also get a decay, but it would probably decay faster, right? Likewise, if the pole was, for example, exactly on one of these imaginary axes, let's say you had a pole right here, we know that the response associated with this would be something like pure sine waves, right? And as you move further down the imaginary axis here, or farther away from the real line, right, the same thing, you'd still get these cosine sine waves, but they would now oscillate faster, right? And heck, we can combine this sort of behavior. Like if a pole was located like over here, right, we would notice that, you know what, you would get a decay, but you would get it in an oscillating fashion here, right? So this thing might look something like that. Similarly, if you came here in the left half plane, or excuse me, the right half plane, you would get exponential growth. If you were further out here, you would get even faster exponential growth. If you were out somewhere like here, you would get an exponential increasing oscillations, right? So we already kind of have a rough idea in the back of our heads of, you know, if the pole locations are in a given area of the complex plane, we know that the resulting performance changes here, right? So what we would really like to do here is formalize that a little bit, because what we would like to do eventually is, if you think about this long enough here, is we would like to have a system here, or maybe I'll draw this as a large box to start off with here, right? Is I would like to have a system or a workflow where someone could come in here and specify some desired performance. So for example, your manager could come in here and say, you know what, your system had better have a specific percent overshoot, a specific settling time, a certain damp natural frequency, etc., right? These are all parameters or performance metrics which are easy to understand what they do and what they actually physically mean, right? If they specify a certain percent overshoot, you know exactly what that system looks like, rather than this sort of hand-waving rough idea of how the system is going to respond, right? So these are sort of like high-level requirements that a customer or a client or a manager might specify to you. And what you need to do here at the end of the day here is, we would like to be able to specify and say, all right, if these are my requirements, what kind of requirements or restrictions, requirements / restrictions are on the poles? So in order to achieve this type of performance, you better make sure that the poles end up in a certain area, right? And this is what I'd like to talk a little bit about today. So you might think about this box here as basically transforming high-level requirements to technical requirements, right? So let's maybe write that down. So this is transforming high-level requirements to technical requirements, right? So this is something that a customer might specify or a manager, and here's something that an engineer can deal with, right? So the reason why this is helpful, right, is because once you have this requirement on the poles, we can now feed that into some control synthesis design here, right? So this would be like a box where you would have another engineer doing controller design, right? And you tell that engineer, you know what, you better make sure that the poles end up at a certain location so they can sit here and try to design a controller. You know, let's just call it a controller that works, right? Or satisfies these requirements here, right? So this is sort of the high-level game plan. Let's look a little bit inside this box here and talk a little bit more in detail of what we're going to do today. So maybe, you know what, let's draw this in another color just to keep everything separate. So what you can do here is, if you think about this long enough, the last lecture that we talked about, in fact, that's the one that I referred you to earlier here, right? Actually, you know what might be helpful? Here, let me just pop up another plug for that video here. You really should watch this previous video that we talked about percent overshoot, settling time, omega n, and all that kind of stuff, because what we did here is, let's come back to the whiteboard, is we said that, you know what, that last lecture where we discussed, it was effectively, we called it time domain analysis, right? Or performance metrics, right? What we did in that last video was we talked about how these performance metrics here for a second order system are actually related to things like zeta and omega n here, right? So let's say zeta and omega n, right? So what we could do here is, if we understand the relationship between the natural frequency and the damping ratio of a system to these items here, we're one step of the way here. So this is what we talked about last time in the previous video here, right? So we know how to establish this relationship. So what I want to talk about today is, let's draw this in red maybe, is now we need to take one more step here. I want to try to establish here what is the relationship between zeta and omega n, right? The damping ratio and the natural frequency to pole locations, right? Because that fills out this entire workflow, and now we'll be in business. So we already have the blue box done from the previous lecture. So today what I want to focus on is just this red box here. Let's figure out how we can establish a relationship between the damping ratio and the natural frequency of a system and the location of poles of that same system, okay? All right, so if that sounds like a plan, why don't we go ahead and erase some of this and see if we can get a little bit more space. All right, so I've erased the board here, and we see now we can get a little bit more specific here, right? The real question we're looking to establish here, or to answer here, is a relationship between zeta and omega n and pole locations, right? Okay, so first, let's go ahead and make the same assumption that we were doing in the previous video, namely here that this is a second order system we're dealing with. Okay, which actually for most situations is a fairly reasonable assumption. A large number of systems can be modeled as a second order system. Heck, even if it was a more complicated system here, right, where you had poles, you know, and then you had more poles out here and things like that here. This might be, in this case, like a fifth order system that I'm drawing here. But if you think about this long enough here, a lot of the behavior is dominated by sort of these two, you know, dominant poles, which are closer to the imaginary axis, right? A lot of the dynamics associated with these poles, since they're so far in the left half plane, they're going to decay and settle very, very quickly. So a lot of the interesting behavior can be modeled by just a set of two simple poles here, right? So this is just a slight side note to say that, you know, this assumption is not as crippling as you might expect here, and a lot of systems can follow this analysis here. So let's assume that we have a second order system. In other words, the characteristic equation for this thing right, can be rewritten in our standard second order form. I don't care what kind of second order system you have. You could manipulate it to basically look like an s squared plus 2 zeta omega n s plus omega n squared is equal to 0 here, right? Okay, so let's just go ahead and solve this thing for the location of the poles of this here, right? Okay, solve for pole locations. I don't know how you want to do that. If you want to go here, quadratic equation this thing, or run to Mathematica, or do something like that. And we basically end up with two locations for poles of this system. Let's call them, you know, like an S1 and 2 here. Something you're going to end up with negative zeta omega n plus or minus omega n square root of zeta squared minus 1. Right? Okay. All right, let's go ahead and add to our list of assumptions here. How about let's just deal with stable systems for now to make our life a little bit easier, okay? What stable implies here, right, is that we're basically going to have to ensure that the combination of zeta and omega n is in the left half plane here, right? So basically the magnitude of zeta and omega n is positive here, right? Therefore, the real part is going to end up in the over there in the left half plane. Okay, and furthermore, let's go ahead and assume here that shoot, I ran out of room in our assumptions. Maybe we should have put some bullet points here. Here's another bullet here. Sorry, this is not using the whiteboard space very efficiently here, but let's go ahead and assume that you know, omega n is greater than 0 here, and zeta is greater than 0 here, but maybe zeta less. Well, tell you what, let's leave it like this for now. This should be fine, okay? All right, so if that's true here, you know what we can do is we can rewrite this a little bit. We could write this as minus zeta omega n plus or minus omega n times square root of 1 minus zeta squared times I, right? All I'm doing is flipping the sign of this, or the order of this, which pops out a -1 here. You can kind of see that square root of -1 just turns into an I here. All right, so the reason we want to write this like such here is because, you know what, let's call zeta omega n, let's call this thing sigma, or it's the real part of this pole location here, right? And then finally, let's call this thing, this omega n times square root of 1 minus zeta squared, let's call this thing omega d here, or the damped natural frequency. So really what we end up with here is the pole locations, S1 and S2, or, you know, if you want to, some people refer to these as like a lambda 1 and a lambda 2 for like two eigenvalues here of your system. This thing could be written as just minus sigma plus or minus omega d I here. So in this case, like we said, sigma is just the product of the damping ratio and the natural frequency, and omega d here is omega n times square root of 1 minus zeta squared, right? Okay. Okay, so graphically here, if we were to plot this in the real imaginary plane, so here's my real and here's my imaginary section here. If I had two poles like, whoops, let's draw them as x's, right? Something like this, right? We see that, you know, this portion here, this is going to be at minus sigma, right? And then up here is going to be at omega d. Right? So, again, you could kind of visualize this here. Why don't we go ahead and draw a line here between the origin up to this pole here, right? And we could think about, how about it extending this line, maybe even a little bit further here, right? So what we might want to consider here is, you see there's an angle associated with this. Let's call this angle theta here, right now. So what I want to do is I want to consider pole locations along this line at angle theta here, right? Maybe let's write that down over here. Okay, so let's say consider poles along line with angle theta, okay? So if I look at this thing on any pole on this line, right, doesn't it obey the, or satisfy the relationship that tangent of theta here, right? What is tangent of theta? Tangent of theta is the opposite over the adjacent. Well, what's this opposite end? Well, again, like you can kind of see, this opposite end, or the distance here, this is omega d, right? And the adjacent side, or this length here, well, I guess technically maybe it's easier to visualize if I draw it down here, right? This length here is just sigma, right? So I think tangent of this angle is just opposite over adjacent here. So this is just simply, what, omega d over sigma, right? Plug in our expression for omega d here, right? Omega d, we said, was here. It's omega n times square root of 1 minus zeta squared, right? All over, what's our expression for sigma? Sigma is zeta times omega n. So look at this, the omega n's cancel here, and we actually end up here with, square root of 1 minus zeta squared all over zeta. This is equal to tangent theta. Or I guess if you want to look at this here, theta is just the inverse tangent of this thing, right? So we could also write theta is equal to tan inverse, right, of square root of 1 minus zeta squared over zeta. And again, hopefully some alarm bells might be going off in your head. Usually when I see an inverse tangent, all right, I always think about a tan 2, right, versus a tan. Right, I think everyone, hopefully everyone is somewhat familiar with this concept here, right, of a 4-quadrant inverse tangent versus a simple inverse tangent. In this case, I think a simple inverse tangent is going to work for our case if we just look at things between 0 and 90 here. But if you want the entire spectrum here of a full 360 degrees, you might need to be thinking about an a tan 2 instead of a tan here. But I think that's a little bit outside the scope of our discussion here. All we're trying to understand here is that, you know what, you end up with this relationship here. Okay, so maybe we should box this up here. And we should maybe think about here, what does this actually mean? If you look at this long enough, what's interesting here is this is not a function of omega n, not a function of natural frequency here, right? So the other way you can look at this is it's basically saying here that any pole that's along the line theta, it actually has the exact same damping ratio here, right? So maybe we should write that down right underneath of it here, right? So what's interesting about this here is that any pole along this line has the same damping ratio, show zeta, right? Or I guess you can think about it in the opposite way too, is if you need to know a specific, or you want a specific damping ratio, that is going to dictate an angle here for this. So let's look at a quick example here. For example, what if, maybe we'll leave this picture up a little bit. Let me see if we can fit in an example here. So, example, what if you want a zeta of, critical damping, 0.707 here, which is actually 1 over root 2, right? If you want to make sure your system has this damping ratio, well, we better calculate what is the angle necessary here. So in this case, then we see that theta that you need here is just tangent inverse here of square root of 1 minus 0.707 squared all over 0.707 here. And if you run this thing through, you basically get 45 degrees here, right? So what that means here is this angle here had better be 45 degrees from the horizontal here. So you better make sure that your pole lines up on this line that's 45 degrees if you want to make sure that you have this 0.707 damping, right? Okay, so that's interesting. Let's take this one step further here in the sense that we could now maybe link this to, say, percent overshoot here. So maybe I got enough room over here. Let's now talk about how about to relate to performance metrics. Right? So if you recall here from our last lecture, right, we said earlier that the percent overshoot of a second order system is something like 100 times e to the minus pi zeta all over square root of 1 minus zeta squared, right? And the thing that was also interesting about percent overshoot, we also see that it is not a function of omega n, right? It only depends on the damping ratio here. So if you think about this, one procedure now that you could do is if your manager specifies a percent overshoot, we see that what they're really doing is they're specifying a damping ratio, right? And if you're specifying a damping ratio, we can now use our relationship here to establish where's this angle or where's this line that you have to fall upon here, right? So let's write this down here. So the procedure now is actually pretty elegant here. So step one here, based on the required PO, right? Based on the required percent overshoot, calculate required damping ratio zeta here by basically what? Back solving this thing here for zeta here. So I'll let you solve this for zeta in terms of PO, but you know, if you want to just take my word for it here, I use Mathematica to basically get us zeta is going to be negative at the ratio here of natural log of PO over 100 all over square root of pi squared plus natural log of PO over 100 squared. Okay, something like that. Let me see, crud, is that readable here? Here? Okay, so great. So your manager dumps percent overshoot in your lap. You just run it through this formula and you see that, okay, that means I have to have a specific damping ratio here, right? Once I've got that, step two here is, okay, based on this zeta that we, or the damping ratio that we just calculated, right? We can go ahead and calculate required angle theta here, right? Using our relationship right over there, right? We said theta is inverse tangent of square root of 1 minus zeta squared all over zeta, right? Great. And then once you have that, step three here is just draw this line here, right? So draw line with angle theta, right? And now make sure that whatever controller that you're using here, or whatever system that you have whatever way you have to move the poles, you make sure that the poles end up on this line. Okay, so draw a line with angle theta and make sure poles end up on this line. Right? Great. So this is a way that based on the percent overshoot, we see that that actually places some restrictions on where you can be in the real imaginary axis. How about, what about like settling time? Is there something with settling time that we can relate now? How does settling time affect the closed, or the poles of a system here? So let's go ahead and look at settling time. All right? Okay. If you remember here, again, from our performance metrics or our time domain lecture here, or the video I was basically asking everyone to watch earlier, we said that, the settling time of a system here was negative natural log of the settling percentage delta all over sigma omega n here. Right? Now, if you remember, we said that zeta omega n is just, we call that sigma here, right? It was this real part of the imaginary pole here. Real part of the imaginary, pole. So, you know what we could do here is, let's just rewrite this here, right? So this is negative natural log of delta all over sigma, right? Or if we wanted to actually solve this for sigma, we could write this as here. Sigma is negative natural log of delta all over the settling time here, right? So this is actually really interesting here, right? Because again, what's going to happen here? Your manager is going to, or your client is going to say, I need the system to settle in a specific amount of time. In other words, they're going to give you the settling time that you need to meet. And they're going to say, I need to settle within 5% of my final value here. So they'll give you delta. So they will basically give you everything on the right-hand side. You can use this now to calculate sigma here, right? And we see what that basically means here is that this places a restriction on the real part of the pole of your system here, right? It doesn't care about the imaginary part. It just places a restriction on the real portion here. So what we end up with here is, why don't we go ahead and just write that down here, so we can say that a TS requirement, right, a settling time requirement, basically places, let's see, or dictates the distance from the y-axis. This is AKA, it dictates the real part of the pole, right? Again, so what that just means here is the pole has to be a certain distance away from this imaginary axis. And we're going to look at an example here at the end to tie all this together here, but I think this is hopefully a simple enough concept here. Okay, that goes and does a settling time here. Maybe let's come over. I wish I didn't draw this thing right in the middle of the board here because it's kind of killing my space here. Let's yeah, let's do it. Let's do it right here. How about let's see if we can use this intelligently here. Maybe I'll just draw a line. Sorry. Okay, so now how about natural frequency? What happens if you specify a specific natural frequency? What I'd like to do now is, okay, let's consider how about poles along a circle of radius r here. So maybe let's write that down here. So consider locations along a circle of radius r. Okay, so let's draw that in blue over here, and maybe I'll try not to mess up this plot too much here or make it too complicated. But let me extend the axis a little bit. Right, okay, so maybe what I'd like to do here is in blue. Okay, here we go. And this thing has a radius of lowercase r. Okay? All right. So from geometry here, what we can see here is that if your pole lies on this radius r here, right, we can say what? We can say that, sigma squared plus omega d squared is equal to r squared, right? That's just the equation of a circle here, right? So we end up with sigma squared plus omega d squared is equal to r squared, right? Or I guess solving this for r here, we could just write this as r is equal to sigma squared plus omega d squared to the 1/2, right? If you remember, what was sigma? Sigma was zeta omega n, right? So it's this thing squared plus omega d was omega n times square root of 1 minus zeta squared, right? Squared to the 1/2. Yuck, yuck. Okay, so again, you could now, let's distribute this through here, and you could actually simplify this. This is a bunch of algebra at this point. Just do all of this, and you know what happens? A lot of this cancels out here, and what's really fascinating here is you just end up with omega n at the end of the day. Right? This is kind of interesting here, because what is this saying here? This is saying here that any pole along this circle here has the exact same natural frequency. It doesn't matter, you know, we're not talking about a damping ratio at this point. It just is natural frequency related directly to radius here. So we see here that, all right, if your manager, again, dumps a requirement and says, like, I have to have the natural frequency of this system to be 3 radians per second, what they're really telling you here, right, you as an engineer can now think, oh, what they mean here is I actually need to make sure the pole is at a radial distance of 3 units here, right? So let's just write this down here. So a omega n requirement actually dictates the radial distance from the origin, right? So you see that they end up being these circular restrictions here, right? Okay, cool. Now, natural frequency, we know that's not actually the frequency that the system is going to oscillate around, right? We know that the damped natural frequency is the actual oscillation frequency. So let's consider that one next. Let's see, maybe we can come over here to this far side. Okay, so the last one, how about our damped natural frequency? Right, omega d, right? Okay. All right. This one's actually pretty simple here because if you think about it, look at this. We already talked about what is omega d. Omega d is actually the imaginary component of the pole here, right? So we can just say from inspection, right, we know that omega d is basically it's the distance from the x-axis, right? It's the imaginary component, right? So we see that if your manager or your client says, you know what, this system, I'm trying to, I want to make sure it oscillates at this specific frequency. I don't know, maybe they're making some kind of, some vibration system that is trying to induce resonance at a very specific frequency or whatever. I don't know, I'm making up some convoluted example, but if they tell you the system had better oscillate at 15 radians per second or you're fired, right? What are they actually telling you, right? That means they're actually telling you that the imaginary component, this pole, had better be 15 units away from the x-axis here, right? Or its imaginary component better be 15 here, right? So we see that an omega d requirement dictates the distance from the x-axis, right? It's, in other words, AKA, it dictates the real, the imaginary part of the pole, right? Fascinating here, right? So this is really cool. So this discussion we've just had, we now have a way to map some of these physical requirements, like the percent overshoot, the settling time, the natural frequency, the damped natural frequency. We can all relate those to where on the real imaginary axis had those poles better land here, right? So let's take a look at an example here of trying to combine all of these together here to see how can we use this simultaneously, right? A lot of the times, and you're not just going to get one requirement. You know, your manager's not just going to say, oh yeah, go ahead and get the percent overshoot to be 13, but who cares about anything else, right? No, they're usually going to say something, I need the percent overshoot to be 20, I need a settling time of 4 seconds or less, and this thing better not oscillate faster than blah, 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 right? Okay, so in that case, let's look at an example of trying to combine here multiple requirements simultaneously. Okay? So in this case, let's say that that your jerk of a boss gives you a bunch of requirements at the same time. They say, you know what, percent overshoot had better be less than 20%. I'm trying to remember if I had a specific. Yeah, okay, so that thing, right? And then settling time here has also got to be less than 10 seconds to within 10% of steady state value, right? And the oscillation frequency, of less than 0.1 radians per second here, right? So they give you all three of these and they say, you know what? Here you go, you better do this here or you got to start looking for a new job here, right? So you're saying, oh, crud, well, I'm really glad I watched this lecture because now I'm going to save my job here. So what we need to do is we need to translate these high-level requirements into pole restrictions here, right? Okay, so let's go ahead and do that now. So the first thing that I would do here is let's take a look at this percent overshoot requirement, right? We talked about this earlier. We saw that this percent overshoot requirement is really a requirement on damping ratio here, right? So what we could do here is let's go ahead and calculate the damping ratio that's necessary. We saw that that was negative natural log of the percent overshoot. In this case, it's 20, right, over 100, all over square root of pi squared plus, whoops, that should be a squared, not a cubed, plus natural log of 20 over 100 squared. Great, so you run those numbers here, and what you end up with here is, where was this? Okay, 0.456. Okay, great, and now that we know the damping ratio that's necessary, I can go ahead and calculate the angle theta that's associated with this here, right? And that again, angle theta, again, just to refresh everyone's memory here, we said that this theta was tangent inverse of square root of 1 minus zeta squared, so 0.456 squared, all over 0.456, right? So you just run this here and you get an angle here of, what's our angle? 62.9 degrees. Okay, all right, so tell you what, let's come here and draw ourselves a real imaginary axis here. Here's our real, here's our imaginary. Okay, and now what we see here is, maybe let's do this in a couple of different colors. So in blue here, let's draw ourselves a line here, kind of on both sides here, right? And this angle here is 62.9 degrees here, right? So this blue line here is our percent overshoot requirement. Okay? And notice here that said, you know what, you need to have, we don't want a percent overshoot of exactly 20. It can be anything as long as it's less than 20. So if you think about that long enough, what that means here is anything down here is actually admissible here, right? If you go further out, you start getting into less. So this line here represents exactly 20. So down here is okay, out here is bad. So maybe what we should do is let's just draw, maybe I'll try to draw this with some blue lines here, right? So blue lines mean inadmissible, right? So blue is inadmissible due to the percent overshoot requirement, right? If you're in these blue crosshatched lines, you're fired here, right? Okay, so let's keep going then. How about taking a look at one of our other requirements? How about our settling time requirement? Maybe I guess let's erase this. All right, we discussed the percent overshoot requirement. Okay, so how about settling time here, right? So we said settling time has got to be less than 10 seconds here. So, all right, so now our settling time, right, requirement, I think we saw earlier what that did was that placed a restriction on the real part of your imaginary, of your complex pole here, right? So sorry, actually we solved this thing and we saw that we end up with, if we're considering settling time, right, we saw that, okay, the real part sigma, this had better be minus natural log of delta all over your desired settling time here, right? Or in other words, minus natural log of 10% here, right? So 0.1 all over our settling time requirement of 10 seconds here, right? So this guy comes out to be, where was it? Here we go, 0.23, right? Okay, so what that tells us now is, let's just draw that line here, right? So there's a line here at x equals 0.23, so maybe something like this. Let me draw it like in a different color here. And right here is 0.23. I guess technically negative 0.23, right? So this basically says that here's the event horizon. Anything over here should actually settle faster, right? Because you're getting further in the left half plane. So this side is inadmissible here, right? So maybe what we should do here is, again, red here is our, maybe how do I want to draw this? Let's draw it down here. So red here is our settling time. Settling time requirement. Right? And now the inadmissible regions is, let's do it in red here, right? So these cross hashes are inadmissible, right? So red here is, again, inadmissible due to TS requirement, right? So this is actually getting fascinating here, right? Now you can see that this region here, this triangle, it would have satisfied the percent overshoot, but it does not satisfy the settling time requirement. So we have to stay in clear white space in order to simultaneously satisfy both the percent overshoot and the settling time requirement, right? Okay, let's do our very last one here, right? We said the last one was this, this oscillation frequency here, right? So oscillation frequency. Right? And we said, again, that was pretty simple here, right? We said right off the bat, if you say that omega d had better be actually less than 0.1 rads per second, right? we saw that this was basically a restriction on how far away from the x-axis you are. So what we can do is let's draw it in a third color, green here, something like this, right? So I'll draw a green line here and here, right? Where it crosses this line here at what, 0.1. 0.1 here, or I guess you can think about it as this distance here, right, is 0.1, right? So the green here is our omega d requirement, right? And again, if I want the oscillation frequency to be less than 0.1, I better be inside these two lines here, right? The absolute magnitude of the distance away from the x-axis had better be less than 0.1. So all of these green regions, right? These are all inadmissible because they violate our omega d requirement, right? So these green ones are inadmissible due to omega d requirement, right? So this is really fascinating here. So we see here that by combining these sections of the real imaginary plane, we can find different regions which are admissible and not admissible in our section. So the only place here that we see that simultaneously satisfies all of these requirements is this green, or this purely white rectangle out here. Right? So let me write this down here. Maybe we can draw this in a, shoot, I ran out of colors. I don't have any more colors. Maybe let's just do it in sort of this squiggly line like this here, right? And I think actually if I had drawn this accurately, no, actually this is actually fairly accurate. If you plotted this out, it would be pretty good here. Yeah, this would be pretty good here. So in this here, this white space is the only region, so you must make sure that the closed loop poles, however you're going to screw with your system here, you got to make sure they end up in this region here. So this white region, this satisfies all three requirements simultaneously, right? And again, what's interesting about this is, you know what? The percent overshoot requirement is actually an inactive constraint in the sense that it's actually not limiting your design here. So the percent overshoot, we could have thrown that away by satisfying these other two. You automatically get the percent overshoot, which you kind of see graphically here, right? So this is a good way. Now I think we see that there is a way that we can now link the performance requirements, these high-level things like settling time, oscillation frequency, percent overshoot, all that stuff, to actual locations in the real imaginary plane of where your system has to end up here, right? So I think this is a good area to stop here. The next video, or one of the next lessons that I want to talk about now, is let's finally combine this with a control design, namely say root locus or something like that, to see if we can use this in combination with a control synthesis technique to actually generate a controller for a given plant that will satisfy all these requirements simultaneously. So I hope you enjoyed the video. If so, please subscribe to the channel because, like I said, we're going to have lots of other discussions on control theory here, as well as some associated computer tools to help us in this process in the future. So with that being said, I hope to catch you at a future video. Bye.